Hi everyone, let's talk about the Archimedes Approximation of Pi. As early as 250 BC, the Greek mathematician Archimedes calculated the ratio of the circle's circumference to its diameter. Now we know that ratio to be pi, but how did he approximate pi's numeric value? That is what we are going to learn today. So let's begin by looking at the main idea behind his approximation. Let's begin with this circle, and let us suppose that the diameter of this circle is 1 unit. Then, since the ratio of the circumference over the diameter is given a name of pi, and if d is equal to 1 unit, then c over d would just become c over 1, and so we now have this value, c is equal to pi. So if we can find therefore the circumference of this green circle with a diameter of 1 unit, then we'll be able to know what's the numeric value of the ratio c over d, which is the pi. So this is what Archimedes did. He inscribed regular polygons inside the circle, and he increased the number of sides of those regular polygons until the perimeter of the regular polygon approximates the circumference of the circle itself. So if we make the number of sides of these blue polygons to be, let's say, 1,000 of sides, then whatever is the perimeter of that polygon would give us a lower boundary for the value of pi. On the other hand, to find the upper boundary of our approximation, we can circumscribe regular polygons around the circle, and the resulting figure looks like this pink polygon. Again, if we increase the number of sides of these pink polygons to thousands up to infinity, then the pink polygon would approximate the circumference of the circle itself. And so that's the game plan. Find the lower boundary and find the upper boundary and squeeze the circle between these two polygons in order to find a good approximation of the actual numerical value of pi. So let's carry out now that idea using some examples. So we begin again with this circle of diameter 1 and of radius 1/2. Then let's inscribe polygons to the green circle. We have pentagon, hexagon, heptagon, octagon, and so on. We have decagon and dodecagon. Now, if we continue increasing the number of sides of this polygon into infinity, then we can have this blue pentagon actually becoming a circle. Now, how can we find the perimeter of this polygon? Let's subdivide the polygon into triangles. We now have here 8 isosceles triangles. Let's bisect this angle here to form a perpendicular bisector like this. The resulting yellow triangle is a right triangle. The hypotenuse of the right triangle is the radius of the circle itself, and the length of the side of the polygon is divided into 2. So this leg of the yellow right triangle is 1/2 the length of the side of the polygon. Let's call the angle here to be alpha, and we can use now right angle trigonometry to find the value of s. Although during the time of Archimedes, he is using pure geometry in order to find the length of the side. But for our purpose, let's use trigonometry. So we can now form this equation. The sine of alpha is equal to the length of the opposite side, s over 2, divided by the length of the radius r. So s over 2 over r, which is just the same as s over 2 times the reciprocal of r, which is 1 over r. And simplifying, we found that s is equal to 2r times sine of alpha. But what's the value of r? We know that r is equal to 1/2, so this becomes 2 times 1/2 times sine of alpha equals s, which is simply equal to sine alpha equals s. So we now know that the length of this side of the triangle is equal to sine alpha. Now, to find the perimeter of the polygon, we can simply multiply the number of sides times the length of one of those sides. So P is equal to N times S. But we know that this S is equal to sine of alpha, so therefore this is now our formula for the perimeter of the inscribed polygon in this green circle of radius 1/2 or diameter of 1. But what is the value of our alpha here? Notice that if this angle is alpha, there is another angle alpha here because we bisected this central angle of this isosceles triangle. And so we now have here an angle of 2 alpha for each of these isosceles right triangles. But since one rotation is 360, we now form this equation. 360 divided by the number of sides is equal to this angle 2 alpha. And solving for alpha, divide both sides by 2 to get alpha equals 180 over n. So replacing now this alpha by 180 over n, we now have this formula. The perimeter of the regular polygon inscribed in a circle of radius 1/2 is equal to the number of sides times sine of 180 over the number of sides. This is now the formula that we are going to use in order to compute for the lower limit of the approximate value of pi. So let's take some values. Let's say our polygon is an octagon. That means n is 8. We now have this approximate value of pi. We have p is equal to 8, which is our n, times sine of 180 over n, which is also 8 again. And this gives us a numerical value of approximately equal to 3.0614674. Now, if we increase the number of sides from 8 to be, let's say, 128 sides, then here is our approximation of pi. 128 times sine of 180 over 128, and that gives us a value of approximately equal to 3.141277259093, which is a very good approximation of pi. And finding trillion digits of pi is more academic than practical. But for many practical applications of pi in the real world, this number is more than sufficient to carry out our tasks. So thank you very much, and we hope to see you again in our next video. Bye for now.